Now, the final question we're going to deal with is page 25, sorry, not page 25, question 25 on page 182. So same section. Question 25, page 182. And there's nothing fundamentally different about this question, but it is still important to be able to reason these things out. And I'm going to use it as an opportunity to introduce why we are bothering with our permutations at all as a separate topic in probability. Now, question 25. 7 children, including one set of twins, are arranged in a line. How many different arrangements can be made? Again, this is another question where part 1 is not marked as part 1. So we have 7 children and we're told that we're dealing with arrangements, so we're going to be drawing our boxes. We have 7 children to deal with. 3, 4, 5, 6, 7. And we're told we are just arranging them in a line, so we have 7 options for the first place we put a child, and then 6, 5, 4, 3, 2, and 1. And we just multiply all of them together, and we hopefully at this point are happy that that's just 7 factorial. And we put that into our calculator, and we get 5,040 different ways that we can arrange our 7 children. Now that's the real part 1. The marked part 1, in how many of these arrangements are the twins always together? So we're going to write out our boxes again, and then we're going to look at our restrictions. So our twins are always together. So 2 of these boxes must always sit together. 1, 2, 3, 4, 5, 6, 7. Now, what we do is put a block around one of our, or 2 of our boxes in this case. And we know that these 2 people, the twins, must always be together. So this box, this larger box, is effectively going to move around as a single unit. So the twins become like one thing that gets moved around. So this is the twins box, and they're going to move around as a single unit. So the twins could be in any of 6 places. So we effectively have 6 children left, because we have this block of our 2 twins together, and then we have the other children. So we have 6 places we could put our twins, then we'd have 5 places left for our next remaining child, then we have 4, 3, 2, and 1, as you would expect. Now, our twins, one of them could be first, or the other one could be first. So we have 2 options for where the first twin's going to stand, and then the other twin has to stand wherever is left. So we have our twins moving as a single block. So we effectively have 6 children left, because 2 of them are bundled together. They always move as one. And then within that group, we could have the twins, one twin could be standing first, or the other one could be standing first, and then the second twin has to stand wherever is left. So in terms of our total number of ways of doing this, we'd have 6 by 5 by 4 by 3 by 2 by 1. That's all of the ways that we can move our children, taking the twins as a block. And then how many ways can we arrange the twins is 2 by 1. So we could write that in an abbreviated form as 6 factorial multiplied by 2 factorial. And when we put that into our calculators, we get 1,440. So that's the number of ways that we can arrange our children when we keep the twins together all of the time. Now if we look at the probability of the twins being together, So the probability, we aren't asked this in the question, I'm using it as an extension. So the probability that the twins are together So P brackets together for our twins would be the number of times that the twins are together divided by the total number of ways that we can arrange our group without any restrictions. Arrange our children without any restrictions. And always simplify your fractions where you can, so you get a probability of 2/7. So 2/7 of the time, if we were arranging our kids randomly, we would get the twins together. Now let's look at part 2 of the question. In how many of these arrangements are the twins always apart? So always apart, they can either be together, like in this situation, or they can be apart. Now figuring out when they're apart directly is extremely messy and would take a very long time. A much, much faster way is to recognize people are either together or they're apart, which means if we take the total number of ways that people can be arranged and remove all of the times that the twins are together, we will be left with the number of times that they are apart. So if we have the total number of ways that we can arrange the children, and we remove all of the times that the twins are together, we will be left with the number of times that they're apart, which is 3,600. So let's write that out in more general terms. All of the ways that we can arrange our children together, and we take away all of the ways that they are together. And we would be left with the ways that they are apart. So all of the ways we could arrange the children, subtract away the ways that they could be together, the number of times that they could be together, and we would be necessarily left with the number of times that they're apart. If we look at our probabilities, probability of apart, twins being apart, would be equal to 3,600 all over 5,040. And when we put that into our calculators, we get that must be 5/7. Now the final thing I want to point out to you is how this would be dealt with in a probability question. The total probability of all of our outcomes added together must always be 1. So if we take this situation, so this is for probability, again separate to the question we've been asked in the book, 1 would be the total of all of our probabilities minus the probability of the twins being together, would be equal to the probability of the twins being apart. Let's check if that works out. 1 minus probability of together is 2/7 is equal to 5/7. And we can see that that is true. So this is going to be extremely important as we move forward. The probability of something happening is 1 minus the probability of it not happening. So 1 minus the probability the twins are together is equal to the probability of the twins being apart. And you can see the underlying reason for that when we're working out our number of possible outcomes.